Hello and welcome back to Data-Driven Methods and Dynamical Systems. So this is a follow-up video to the pseudo-inverse that I was talking to you about, and here we're going to take a look at how you can use an algebraic reconstruction technique in order to recover a the original how you can recover the original data from the Radon transform or its sinogram. It's like nearly midnight, so maybe it's appropriate to use this intro. Okay, so I apologize that it's taken me a few days to get to this. I've been wrestling with the code for a long time, for probably like the better portion of 2 weeks, and then today it just occurred to me that I was being really stupid. So yeah, the Radon transform, pretty straightforward. Basically, it is a integral across a single line from negative infinity to infinity of a function. Usually a function that we assume is, say, compactly supported, or it decays fast enough for the integral to exist, or something like that. Compactly supported is usually well motivated in most cases because a person or an object inside a CT scanner really only takes up a certain amount of space. So so that is usually a good assumption that we can run with. And then the inversion of the Radon transform happens through the filtered back projection algorithm, and that's something I covered in my last class, and don't worry if you don't know it, it's not something you're going to need here. This is a completely different direction that you could take with the inversion process. Now, the proper inverse is actually the filtered back projection, but you can also use straight linear algebra to do it. Now, algebraic reconstruction techniques basically pretend like everything inside the scanner can be broken up into pixels. And so it separates the image into a whole bunch of square pixels, and then it computes the Radon transform through each of those pixels, and then tries to reconstruct the original object back from those. And so this involves a very tall matrix times a collection of weights for each of the pixels equal to a very tall vector, which corresponds to all the individual Radon transforms for the individual t and the individual theta. If you want a recap of the Radon transform, that I have a lecture in my tomography class that happens fairly early on, so if you want a review of that. But for running the code, it's not going to be too bad. We can go ahead and put it together. Now, what I was trying to do is I was trying to take the Radon transform of squares and make them really tiny squares, and then take the Radon transform of that. And I bumped into a lot of issues in that I was trying to I was bumping up against the conventions that MATLAB took, MathWorks took, when they were designing the Radon transform, and it wasn't exactly clear how they're organizing their t's and their thetas and so forth. And so I try to use my own Radon transform code and try to finagle something out of that, but then that ran into its own problems, because guess what, you don't want to reinvent the wheel, especially, and that's like rule number 1 of rapid prototyping. So instead I decided to do something a little bit more clever. So what you can do is you can just use the Radon transform for each individual pixel. So basically I make a whole bunch of square matrices, and I put a 1 where I want that pixel to be, and then I take the Radon transform of it, and then I move the pixel over, and I take another Radon transform. I move the pixel over, I take another Radon transform, and then I turn each one of these using the reshape command into a column vector, throw them into the matrix A, and then basically when you multiply all of these columns times the weight vector, basically the weight vector is going to try to tune each one of these until they match the actual samples they took on the right hand side, and then you can go ahead and invert it. Now if you're doing this straight like this, using simulated examples will give you a perfect reconstruction of your it'll give you a perfect reconstruction of your of the original object. And that's nice. But there are drawbacks to it, and one of the biggest problems is just the amount of time it takes to process all these. So the filter back projection algorithm, the reason why it's favored is that it's fast. It's really, really fast. It doesn't require a lot of memory requirement. It doesn't require a lot of memory, and so you can use FFT and you can just reconstruct your entire function pretty quickly. Whereas with algebraic reconstruction techniques, they blow up very, very fast. You can't really do them for very large images. But they do have their advantages, and one of the advantages that they have over over the filter back projection is that algebraic reconstruction techniques can still work if you don't have the full range of theta values. And so if you want to limit your exposure to or patient's exposure to radiation, you can limit the number of angles that you take the actual images at, and then try to reconstruct, even despite having much fewer than what you usually would need. And this is what leads you to something called compressive sensing, or L1 regularizations and lasso and all these things to exploit sparsity in your solution in order to get the most out of it. And we can talk about that later. But for now, let's go ahead and talk about algebraic reconstruction techniques and how to actually implement them. And we'll try to throw in a little bit of noise and see what happens there, and also toy with having very, very few angles. And we'll see how we can exploit using the SVD to get an inverse, sometimes even when we don't have necessarily a very tall matrix, but maybe we have a very squat matrix, and we still need to get the best that we can out of it. And so the pseudo-inverse will help us there. Now, the pseudo-inverse we can actually compute very quickly just by, instead of saying INV of a matrix, we put P INV of a matrix, and that'll give you the full pseudo-inverse that you would get using a more Penrose pseudo-inverse. But we can also play with truncated inverses, where we don't actually use the entire SVD, but we only use a portion of it. And so, and you can get sort of these low rank approximations of your original image that way. Okay, so let's go ahead and jump into it, and I might have built up way too much for myself to do right now at this time, but we'll see how it goes. Alright, let's see. Okay, so I'll switch over this microphone, and yeah, we'll go ahead and get going. So this is the carnage I left here. We'll just go ahead and start a new file. So I'm going to say size of image, and I'll make it 64. So I'm basically looking for a 64 by 64 matrix here. Now there's this thing called that we call a Shep-Logan phantom, or just phantoms in general. But the Shep-Logan phantom is probably the most famous and commonly used one, and it looks like this. So there's a phantom command. If you haven't installed the image processing toolbox yet, you really should, because this is you're not gonna be able to do any of this without it. So yeah, if you can, go ahead and get that, and that'll be good. Let's see. Try to rearrange things a little bit. Last time I left the microphone on the desk, it caught all my hacking away at my keys, and so that made the audio completely unusable. So instead, try and put a buffer over the computer. And I'm tired, so I'm not going to type as fast, so we'll see. I should stop laughing. Okay, so here we go. So a phantom, what is a phantom? So I'm just going to put phantom, and we're going to say size of image. If you just put a number in there, it gives you the Shep-Logan phantom automatically at this size there. But phantom can also take a matrix where each row describes an ellipse of some kind, and so you can actually build your own phantoms using a custom collection of ellipses. But the Shep-Logan phantom is a standard one, and so if you want to see what that looks like, we'll do image show, SL phantom, and we'll just use this to resize the values so it looks nice. Okay, so I need to save it. So algebra down. Here we go. All right, so this is Shep Logan Phantom at 64 here. And so this is a pretty small image. I mean, nobody wants a 64 by 64 image, but getting much larger than this is going to really choke us. We can do work with larger images, but they take time. So, but here we go. So for quickly showing how this works, we can do this. Okay, but that's not the actual data that we're going to be dealing with. What we get from a CT scanner is a sinogram, and so instead of just taking the image of the phantom, I'm going to actually take the image of a sinogram. And so we need to use the Radon for this, so I'm going to call this the SL Shep Logan sinogram. And so what we get, so this is the Radon transform of SL Phantom, and I need to have some theta values. So what is my theta values? These are going to be the angles that the CT scanner should take when it's constructing this. And so we'll just start with the very standard 179. This is actually what MATLAB does by default. And this is angles in degrees. We are not going to have to worry about that, not like I was fretting over it earlier. So so this is simulated CT data. Okay, so so what does this look like? So image show SL sinogram. Let's see what we get. Let's say. So let's comment this one out and see what this is. All right, so this is what a sinogram looks like. So basically each one of these points is a result of a Radon transform, where the Radon transform was taken at a certain angle, where basically the line was arranged at a certain angle and the angle is indexed here. And so so if you think of a ray coming out of the origin in standard position, so so basically I guess for you guys it would be this way, and the length that is going out is t, and then you rotate it as theta goes, and so you're looking at a line that's perpendicular this way. So a theta, so for instance, if I were to keep t at 1 and I choose theta to be 0, then we're going to have a vertical line going through the point 1, 0, right? And if I choose theta to be 90, then it's going to be a horizontal line going through the point 0, 0, 1. So so that's what we're seeing here. And so so basically this is t ranging from some, I think, negative 32 something up to positive 32. I was a little confused about how MATLAB did this, but I know it starts on negatives and it goes up to the positives. And so I was thinking, so right here should be right where the dead center of whatever object you're looking at is. And as we go along and check out each column corresponds to a different angle of the CT scanner. And so so basically this whole strip here is basically the result of like one X-ray. So each column is a result of one X-ray. Now usually you'd have multiple columns, and then you basically will have this over and over again in a whole bunch of layers, and then you go ahead and you invert it, but we're only doing one slice. So but yeah, so that's a Radon transform or a sinogram. So yeah, let's comment that out. So now let's see next. So the next thing we need to do is we need to figure out how we're setting up this matrix. So basically what we're going to have is we're going to have some A times W. It should be equal to P or B or whatever we want. And this P value, I think in the lecture I said B. Let's see, but let's say P. So essentially P is a column of our Radon transform. So basically we're going to spool that sinogram that we just saw out into one gigantic vector. And then we are going to, A is going to be as tall as the spooled out Radon transform. And W is going to be the height of W is going to be the total number of pixels we have here, and so it's going to be 64 by 6 times 64, and so that's what, like 2 to the 6 squared, so that's what 2 to the 12, so it's what 1024 is 10, 2048, so 4096 should be what we're looking at. So W should be 4096 column vector. All right, and that makes A 4096 wide. Okay, so how are we going to do this? So I realized that what I'm going to do is it's better to just take a matrix approach, and so if you look at what we get out of SL Phantom here, so what we got out of the Phantom, if I just go ahead and plug it in here, there's nothing magic about it. It's just a matrix, and so what I'm going to do is I'm going to make a matrix. We're trying to reconstruct this, right? And so the idea is I'm going to make a matrix. It's going to be, say, 1 here, and then 0 everywhere else. I'm going to make another matrix that's 1 here and 0 everywhere else. And the idea is that we can take the linear combination of sinograms of each of these guys and make the sinogram of this guy. So, for instance, if I take B1, let's say B is equal to zeros, we'll say size of image. This makes a 2 by 2 grid of zeros, and I'll call it, say, B1, and I'll call it, say, B2 is equal to zeros, size of image. So these are 2 different 0 matrices, and so I'm going to take B1 to be, say take 30 comma 20, and I'll set that equal to 0, and with B2 I'll take say 21 and 10, and I'll say that's 1, and everything else is 0. And so what we can do is we can go ahead and say take a Radon transform of a linear combination of these. So I'm going to say Radon of say imshow. I'm not going to save this, so I'm going to take Radon transform of B1 plus 0.5 times B2. So this is just a matrix. It's an image with 2 pixels that are not black, and I need to give a theta value. So say theta, comma, and then normalized, and there we go. So let's see. So I'll take these guys, and let's go ahead and next evaluate it. And there you go. So the idea is that each one of these square pixels is going to give us a little trace through here. And what we're going to do is we're going to try to take all the possible traces that we can, all 40,000 of them, or whatever, or all 4,000 of them, and that's going to give us a whole bunch of different traces through here, and then we can fit those to the original image. And once we do the fitting, then that tells us what the weights had to have been for the actual square pixels, and then we can just get rid of that and just get rid of the Radon transform fitted, and we're going to go ahead and just display the pixel values themselves. So, and that's more or less all we need to do. And so in order to do this, we need to go through and we need to actually make these. So I'm going to start with B is equal to zeros and size of image, and so just like we had before. Now for let's see, I equals 1 to size of image, and for J going from 1 to size of image. Let's see what we get. So first of all, at IJ, I'm going to make this 1. But I really should also make the last one 0. So the idea is I'm going to be sorting through here. I don't want to make a whole ton of matrices, so I'm just going to go in here and toggle 1 and 0 as I go. So I'll say last I and last J, this should be 0. And I need to define what last I and J are. So I'll say that. Say last I and last J should be 1. I don't even know what I'm typing there. That's late. Last I was equal to I, and last J is equal to J. All right, so this is going to come at the end of the code there. then we'll close the loop, and then we need to say last I is equal to 1 and last j is equal to 1, because it'll complain if we don't have something to start here. Okay, so now what do I do? Well, what I'm going to do is I'm going to make a radon transform. I'm going to take the radon transform of B at these theta points. All right, now what do I do with that? Well, I need to put it into a matrix. I need to figure out what A is. Well, I already told you that A should be the size of this sinogram reshaped, so let's say zeros. I don't know what that is yet, so I'll leave that blank for a second. But I do know it should be as wide as the size of image squared. Right, so size of image only accounts for the length or the height, and so the total number of pixels is going to be that squared. All right, and so for the sinogram, I'll say SL sinogram column, and this should be reshaped matrix. So you just, for reshaping a matrix, you just take a matrix, SL sinogram, so that is a matrix of some kind, and I'm gonna not tell it, I'm not gonna specify a height, because I'd like to be able to change the code at some point. But I'm telling you I only want one column, and what this does is it forces it to figure out the best fit it can to make everything into one column. And so basically it's going to take each one of the columns and it's just going to stack one on top of the other all the way down. Right, and so then this should now be the length of the SL sinogram column. There we go. Okay, so now turns out I can just use this code again, but it's just going to be on B. Or rather on sinogram for B. So put this in here, and I'll take this, kill off those, and boom. Oops. Oh man, I copied it. Alright. Slip the fingers. There we go. And kill this. There we go. Okay, good. So now I took B, I did the same deal. I spun it out and stacked all the columns for radon transform. Now I need to put it somewhere, and so I'm going to put it in A. And so I'm going to make the entire column of A equal to this. I have some index here, which is index B. Well then, let's see. So I'd like to basically, as I go down, just like with the radon transform, I want it so that I start at the top left of an image, and then I work down one pixel at a time until I get down to the bottom, that I go up to the next column. I think what I need to do is this. I need to write size of image and multiply that times I minus 1 plus j. And so I think that'll end up working. Yeah. That's what I'm going to try. We'll see. This is just some number theory trickery that I'm doing in here. Not even really that much. But basically, j runs from 1 up to size of image. And once it finishes running, I increments by 1. So this is like, counting to 10, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then once you go to 10, another number increases on the 10 position, right? And so that's the same sort of thing that's going to happen here. J goes from 1 up to the size of image, and once it reaches that, we increment I by 1, and then we do the whole thing over again. J falls back down to 1, so J is never 0. But that should end up working. Let's see. So once we have that, that's it. We're done. All we need to do now is figure out what W has to be. What we could do is we could just do this. We could say W is equal to P inverse pseudo-inverse of A against the column, right? And that would do it. I could probably run the code right now. And in order to show what W looks like, I would say image show, and then I just need to reshape W to be what it should be. So W equals size of image, comma, size of image. So in this case, I'm not leaving it up to chance. I'm specifying exactly the shape I want it to be in. And then for image show, I put this so it rebalances everything if necessary. And so yeah, so let's see. Let's give this a run, see what we get. Oh no, I can't run it. Reshaped. Oh, reshape. Should be like that. All right, let's see. And I copied that one. So there we go. Okay, let's see what we get. If all works out well, we should see exactly the Radon transform pop right back out. Or sorry, not the Radon, the original image pop right back out. So the Shep Logan Phantom. I remember that was like basically a circle with a whole bunch of ellipses in the middle arranged. And there we go. Okay, so maybe my choice wasn't the best. It came out sideways. So I think if I change this for J, and I change this for I think that would probably take care of everything. Give it a second and we'll see. Anybody else tired? What time is it for you guys? What time do you guys watch my videos, huh? Maybe post that in the comments. If you made it to this internal video inside of the other video. I mean, yeah. There we go. Yep, so that works. So that's the Shep Logan Phantom. It came back and look, it's pixel perfect. And that's because A was full rank and everything worked out nicely. Now, we don't always want exactly to use the pseudo-inverse. There might be a lot of reasons for that. There might be noise that we don't want to reproduce the noise exactly. Having a perfect fit isn't always good because you'll reproduce a noisy signal. And so what we can do is we can also use the SVD. So if I take the SVD of A, and to save myself a little bit of computer memory, I'll put the economy version. This basically will make it so that S is not a rectangular matrix but a square, and it means that you don't have to, you stop adding U's after a bit. And so then what you can do after that is basically we would like to compute the pseudo-inverse. In order to make the pseudo-inverse, we basically need to take S and manually take the reciprocal of everything. We could try to do the pseudo-inverse procedure on S, where you take S prime times S, and then that becomes invertible, and then you take you make a pseudo-inverse out of it. So it's a S prime times the inverse of S prime times S. But it might not actually end up having an inverse, and that'll happen if some of your singular values are 0. So that means that you need to go in there and with your eyeballs look and see if there's going to be any zeros in there. And when I say eyeballs, I of course don't mean with our actual eyes. So I'm going to basically do this. So for I going from 1 up to the length of the diagonal of S, and what I'm going to do is I'm going to basically do this. If SII is not equal to 0, then I'm going to write inverse of SII is going to be equal to 1 over SII, and else end and end. And what is inverse S? Inverse S is equal to zeros, and I want it to be the same size as S. So there we go. All right, so that's the inverse of S, and now instead of computing this, I'm just going to make a pseudo-inverse. Now you remember A should be equal to U times S times V star, right? So here instead it's going to be V times inverse S times U prime, and that should end up giving us what we need. I think I mentioned it in the lecture already, and so if that's fresh in your mind, then great. But for me, it's been like a week since I made that one. Anyway, so what I'd like to do is I'd like to include a truncate parameter. So I'll put inf right now. So usually for truncation, I will keep all the rows, but we want to change the columns. And so you can say 1 to something like 12 or something like that, right? But what I'm going to do is I'm going to say I want it to be the minimum of the truncate parameter, or end. So end inside of a vector always means the last entry of the vector. And so I want to make sure that I'm not going to exceed the last entry here. And so I'm going to take this and I'm going to hit it over here. But this guy will need it in both entries. And then for you. Same thing as this guy. And here we go. So put it in this side of the prime. And there we go. Okay, so give it a quick test. Let's go and evaluate. Oh, Inverses did not. Yeah, right. Have to actually do it. Okay, this is going to take about. Okay, so sorry about that on the camera. It stops recording at 30 minutes. It's some sort of European trade thing. Basically, if you're going to sell something in Europe, a camera in Europe, if it records more than 30 minutes, then it makes it a camcorder, and it makes it way more expensive. So I have a regular DSLR camera that also records at 1080p or 4K, but they have to stop it at 30 minutes. It's really frustrating. Anyway, I don't think I missed it by much, but I'll stop laughing. Okay, so we can see that we were successful in this implementation. It gave us back exactly what we got before. What happens if we use only, say, truncated at 1? Let's see what happens. So we just get this like big circular blob, and this blob has very little to do with our data. We're not using it. It's basically all this is the first singular, first rank 1 approximation, or the best rank 1 approximation of the matrix A. That we got times some scalar value coming from the data, but a scalar value increase or decrease isn't going to make much of a difference. It's always going to be the same shape. And so, but we'll start seeing something more meaningful if we even just take it up to 10. And so, boom. Well, maybe not as meaningful as I thought. All right, let's take it up to. Let's see, what is W? W is a 4096 vector. Let's take it up to 1%, so 40. So we get. Still nothing meaningful. All right, so 10%. Nope, still waiting for something to happen. And let's take it up to 2,000. Let's use half of them. All right, now I'm starting to get a feeling I'm doing something wrong. Let's see. Oh, wait. Oh, that was stupid. Here we go. I don't know why I started putting the column there. It's late. All right, let's go back. Check out 140. There we go. Okay. Sorry, that was just dumb. Anyway, so here we go. We're starting to see something. It looks kind of like a cow's head or something. Or maybe a pig snout. But you started seeing a picture result. I'm just curious what we got at truncated 10. If I did it smart. So yeah, so you get something that's sort of more blobby there. But then if I take this up to, say, 400, so using 10%, then you practically have the image there. You can make out all the major features. You can see that there's something going on here, there's 2 dark spots here, and a big ring that's supposed to simulate a skull. So, good. What happens if I take it to 2,000? There, it's practically perfect. And then again, of course, if I take it up to use all of them, I'll get exactly what I was looking for. So now something we can try. I haven't tried this yet, so we'll see how this ends up working. Let's take the sinogram and we're going to make random noise. So see, don't remember exactly how this works. So help rand. What do we get? So rand n returns n by n matrix containing pseudo-random values drawn from standard distribution on the open interval 0 to 1. Okay, good. So, and then mn, there you go, that's what I need. So, let's see, so, so what I'm gonna do is I'm gonna take here for a sinogram, random, and I'm going to say size of SL sinogram. Let's see if that ends up working. And for this, what I'm going to do is I'm going to take SL sinogram noise, and yeah, so it's going to be SL sinogram plus 0.01 times random. So the largest value in here is 1, so now the largest value is going to be 0.1. And let's shift it down so we get positive and negative. So it's a mean of 0. Okay, so and now I'll take this guy and I'll throw it into my column. Let's go ahead and see what we get. Did not like that. The size of inputs must be integer. There. Okay, now we wait. Now the next lecture, I'm actually going to talk about how we can use what is called kernel PCA in order to deal with noisy images, and it's actually used in medical imaging. All right, so let's see what we end up getting. So this actually ended up being not too bad for us. You can see there is some irregularity, noise and stuff like that coming out of here. The noise wasn't actually all that bad. Let's crank it up a little bit. And but yeah, kernel PCA is used to decompose noise in medical images and in a lot of other places. And basically, the idea is that PCA extracts the principal components, or the components of your data that corresponds to the largest variation. And so yeah, so it'll save. It should be able to recover a good amount. But okay, so here we're starting to see it's problematic. We've lost all the tiny features that were lingering around here, and all of this. And so what I can try to do is I can try to truncate it, and maybe we can just get the essential elements here, and let's start at the 10%. So you see, this 10% area, I mean, it's not the best picture, but it isn't as affected by the noise as the other ones were. And so if I'd say maybe change this up to 2000, you know, maybe that'll end up being able to get around a lot of the noise that we saw. And so here you go. So we saw with the 4000, this little sphere here and this little guy here, they were completely gone. And these are supposed to be here. This, and this. And this are all supposed to be actually in your Shep-Logan phantom. But when we used the entirety of them, let me just make it so that, let's see, truncate, let's change that to inf, and we'll make a new figure. All right, so if I go ahead and run this, let's get a comparison. So here, you can't really distinguish those circles from the noise. So here we're using the complete inverse, and it was a proper inverse of the matrix. And so as far as the matrix is concerned, it's doing a good job. So using the same data, the same noisy data, we have here, using the entire inverse, we actually got a whole bunch of bad noise here. There could have been something here, but it's not really clear if it's differentiated from that nastiness that we see elsewhere. But in this picture, we see that there was a circle here that you can't make out here. There's a circle here that you can't make out here, and there, and there, and yeah, and then this as well. And so these are actually features that were in the Ship-Logan Phantom, and so by actually using a truncated SVD, we came up with a pseudo-inverse to our problem that did better than the actual inverse that we had from the dataset. So yeah, and so that's a win for the SVD, and I think this is where I'll end up stopping it here. All right, thank you for watching, and yeah, I'll catch you next time.